How's everyone doing this morning? Well, we're moving from money to a little bit more of a heady topic. We're going to be talking about the future of computing. Da, da, da. I am going to be guiding this discussion, but certainly not an expert on this. My name is John Shieber. I am a senior editor with TechCrunch the last time I checked, and I write about all sorts of stuff. I also like to make these kinds of panels as interactive as possible. So if y'all want to pose questions to my esteemed panelists so I don't have to and can do less of my job, I'd appreciate that. You can tweet at me at @jshieber. That's JSHIE, B as in boy, ER. If you have any questions you'd like to pose, if they are great, I will ask them. If they are not, I will roundly mock you. That's the way that works. I actually won't. I'm a nice person. I'm very nice. But let's get into it. We have a lot to talk about because the future of computing is an insanely big topic, and we have a great group of people to talk about it with. To my immediate left is Jeffrey Black, my brother from our corporate mother at Verizon Ventures. Daniel Docter, who is, oh no, that's not, yes, Daniel Docter, Managing Director at Dell Technologies Capital. To his left is Dave Johnson, Managing Director at Intel Capital. And then last, but certainly not least, is Mike Redding, a Managing Director at Accenture Ventures. And Mike, I want to start it off with you, if you don't mind, because I really hate to admit it, because I don't like giving consultants props about anything, but y'all have a very interesting way of thinking about the future of computing, which you call the DARQ acronym, the DARQ. Can you tell us a little bit about what that stands for and what that means for compute?
Sure. So as we take a look to the next 3 to 5 years of technology, we think we're entering what we're calling the post-digital era. So we're going from SMAC to DARQ. So from social, mobile, analytics, and cloud, which has been the last 5 to 10 years, to DARQ, which is distributed ledger. I like to say the artist formerly known as blockchain. AI, the R, we had to cheat to make a cool acronym, is extended reality.
See, there you go.
And Q is quantum. Right? And so we think that all of those represent a pretty big shift from where we are to where we're going next. And in particular, the distributed ledger and the quantum, you know, when you start to think about the fundamentals, those are some of the fundamental building blocks of the next wave of enterprise compute.
And I think when you think about artificial intelligence, it'll fit in there somewhere as more of an application rather than like a fundamental infrastructure layer. But to that point, there are man, this is such a great panel. They did this really well. There are hardware and sort of infrastructure issues that are going to play into the development of all of these things that I think someone at Intel would be able to speak to. So when you think about things from the chipset perspective and how that's going to power this next generation of computing, what are some of the issues that you see, and how are these companies sort of addressing it beyond the simple CPU, GPU paradigm?
Yeah, I think there's a big opportunity. Companies are driving a lot of new applications and trying to accelerate new workloads. AI is probably our biggest focus right now, is how we accelerate neural network computing. And you see a variety of computing technologies, IPs, if you will, that are coming into computing platforms. So now if you go to get say a data center compute system or an IoT compute system on the edge, you're going to find your general application processors, but you'll also find programmable logic like FPGAs. You find neural network accelerators that are optimized for that. You see GPUs. And what we're seeing is just a big, really mashup of all these acceleration technologies in the systems, and it's also happening at the chip level. So you see all these IPs being reduced to IPs and integrated in the chip, in the SoC, so you essentially have one component that can do all these things.
And why is that stuff, why is it necessary to create this new chip architecture? And we're going to get to y'all, don't worry about it. It's time for everybody. But why is that sort of stuff necessary?
It's just, the workloads are vastly different. For a lot of visual processing, GPUs, just the floating point type processing is required, and you might have streaming data that takes another type of processing requirement. A lot of very sophisticated customers, like you imagine an AWS that has very, very deep research and development capability, developing their own algorithms and wanting to be able to embed those in an FPGA in a data center rack, right?
Right.
So this is just responding to increasing market requirements.
And I'd
Yeah.
like to get
Yeah.
to that at some point, the kind of chip development work that Google and some of these other companies are undertaking themselves to develop these proprietary chips and the role that that will play. But with Dell and the kinds of things that y'all are looking at, I'm trying to move up a stack, if you will, around compute. So,
but don't. Staying down there at that level. It's a good place to stay.
really? Is that? I mean, are y'all seeing the best opportunities there, or when you?
Well, I mean,
about
we were the outside lead investor for the Series A in GraphCore,
right?
Which is a really disruptive company that's developing AI machine learning focused chips, as are many companies are doing that. And they're now a unicorn company. They just raised a Series D, through 2.5 years, later. But the question,
200 million. How much was that?
They raised 200 and some million at a $1.7 billion valuation. It's all public.
Just 1.7 billion.
Yeah, right. So this is so. But I think sorry, following on where you were going.
Yeah.
I think as you think about the title of this, the paradigms of compute. Clearly, the nearest at hand paradigm is artificial intelligence or machine learning or deep learning,
right.
And every single software in use today is going to be redone in the next decade to be driven by some form of an algorithm or a neural network.
Right.
Not necessarily a brand new one that people are going to invent, but algorithms and networks that have been around for 20 or 30 years, but now have the ability to actually be useful because we have a huge amount of data that we can use and consume that we never have had before, and two, we have compute power and IC and semiconductor technology that is so powerful it can actually take advantage of it.
Well, so first of all, I like how you did A and 2. That's solid. That was a solid move. I respect that immensely. But I think all of this gets to kind of there are two things going on. One, there's a lot of new innovation on the hardware side that's driving more compute power to the edge of the network. Oh man, I'm very proud of myself for having done this. To the edge of the network, and then there's a sort of countervailing force, which is everyone wants to do things off-prem in the cloud, managed by someone else, either AWS or someone. And this is where a company like Verizon and the work that Verizon's doing around 5G fits into all of this computing paradigm, right? So you've got this movement between we want more stuff on our devices, we want to own more things ourselves and do more of that processing ourselves, or do we? And what's your take on that?
Well, I think historically, at least my opinion, is things have kind of waffled back and forth, right? So first there was data centers and computers that were huge and you couldn't take them with you, and then there were smaller devices, you take them with you. Then cloud allowed you to access supercomputers remotely, and we keep going back and forth. So it's, I think 5G is a way to enable kind of the next pendulum swing, if you will, so that now you can do things that in the past you would probably need the compute power very close because you need that real-time processing. And 5G and the mobile edge compute platform will allow that to happen more remotely. So now devices don't have to do as much locally, which is battery consumption is always an issue. So there's just opportunities to kind of change the paradigm of how mobile computing operates.
Now, does that align with the vision that y'all have at Intel and Dell, or do you think that you're not going to have a dumb device where everything lives entirely on the cloud and it's a matter of a fingerprint and phone?
My guess is I'm going to let Dave talk about Foghorn, which is one of our portfolio company we have in combination. But I would say that yes, that's a vision that I think everybody shares. One thing it's still not clear yet is how people are going to make use of that compute. But there's absolutely going to be a continuum of compute from data center to edge. An edge can be defined as the device that we all hold in our hands, or a sensor in an industrial, network, or some localized or very close to the edge, but relatively powerful, compute capability, right? That is distributed at edge. So, we're another investor in a company called Packet, based out in New York, and if you think about what Amazon is, which is hundreds of data centers around the world with millions of servers in them. Think about the kind of the reverse over there is how do you have millions of edge locations, and each of those edge locations might have hundreds of servers in it. right? How does Uber or Tesla take advantage of 150 different data center locations at the edge in New York City?
Right.
Which is what they're going to want or need to deliver the applications to all of us that we're going to want or need.
I mean, doesn't some of that stuff need to live in device, though, when you think about things like autonomous vehicles and the decisions that these kinds of new connected computers are going to have to make on the fly? Can 5G handle that kind of decision-making capacity and the data that needs to flow back and forth between sensors and a device in real time? I mean, what are y'all's thoughts on that?
I'm going to let.
I'll jump in. I'll say, you know, possibly, right? Because it's going to be some pretty large-scale bandwidth. But there's, you know, it's like the human being, right? Our nervous system. When you touch a hot stove, you don't have to think about it. You move your hand because it's a local loop. So an autonomous or assisted driving, where you want to not hit the kid running in the street in front of you, you're not going to. No matter what, you're probably not going to beam that back to headquarters to ask the question. You're going to decide. You're going to decide locally. So I think it's going to be that continuum, and things that are reflexive or really heavy bandwidth where there's no value in shipping the data because you can make the decision local. So it's going to be application specific where the value is in local, not central. You'll make that choice. But the good news is, I believe with 5G, you'll have the luxury of being able to make that choice. Whereas today, because you don't necessarily have that kind of ubiquitous wireless bandwidth, you're kind of forced into one end of the spectrum or the other. You don't have that flexibility. So if anything, it opens up the designers to a lot more creative business solutions.
I think there's a couple use cases that help illustrate where things are going between cloud and edge. In some cases, you do have industrial type situations, or you're working with data where somebody doesn't want to send that data to the cloud, either privacy concerns or security concerns. Industrial tends to be one of those. The other is digital security and surveillance, where you might have smart cities example, somebody pulling multiple video feeds together, trying to run video analytics or computer vision on that, and you have so much bandwidth, you just simply can't take it all to the cloud. So that creates a lot of opportunities. I also think the autonomous driving case is really interesting, not just for autonomous driving, but for other applications. Anytime you have, say, a mission critical type of control requirement, you need closed loop control of a system, and this goes back again to industrial. The ability of a compute system to know exactly when something has to happen, to have a closed loop, ultra low latency control loop to make sure that the brakes go on at the right time, I think is another really fascinating area of compute that you're going to see developed over time.
Well, it's interesting that you bring that up. Just today there was an article, or a couple days ago there was an article in the MIT Review about Triton, which is this new malware that's been infecting industrial facilities and turning off like critical safety components, which means that you can have, you now have hackers who can literally induce a chemical spill or a gas leak at any industrial facility now around the world. Not to creep everyone out, but just to let you know there are hackers that can create the next Bhopal, India disaster. So good stuff, right? Dow Chemical, toxic dump, all of that. Great, hackers, compute. Where I wanted to go with that was sort of how do you see securing this new compute paradigm as part of the equation? Where are the opportunities that y'all see around that? I know that's something I think that you're looking at, right?
Sure. I mean, security is always critical. I think as we look at this next, we're talking about high performance, so the balance is always how much security versus degradation to the quality or the speed of the network. And a lot of, I think there's going to be a lot of adjustment on how we do security in the future. I think blockchain or distributed ledgers are a way. Again, I'm not a scientist, but I kind of look at it as it's harder to spoof or attack one thing, but if you have to, deal with everyone's phone here at once to know whether or not it's valid, that's a lot harder to do. So it's really just kind of, but everyone knows how you're doing it. It's just impossible, or it's much more difficult to do functionally. I think it's almost like bringing it down a level of kind of just saying, well, here's everything, but in order to fake something, you have to change everything.
Right. And Daniel and Dave, where do you y'all see blockchain or distributed ledger technologies playing a role in how you think about this future of compute?
Yeah, one area, so one of my portfolio companies called Filament is applying blockchain to edge devices, and in a lot of cases you have edge devices that are need to enter into what we call an economic contract. Somebody has a piece of equipment that they're say using on a construction site for 5 hours, but you're in a place where you can't easily connect to the cloud and authenticate and have a trusted sort of tracking mechanism. You can use a distributed ledger on the edge across multiple devices to actually allow that piece of equipment to be used by multiple parties, and then track who's using it and drive your billing and everything based on that. But
to jump on that and actually to mash up a couple of your points, filament is used by SpaceX to secure the telemetry during launches. So not only, so people say, oh, distributed ledger is not performant. Actually, however many Mach, 107 or whatever those rockets are going, that's as real time as you get. But they need to know that they can protect critical infrastructure, that no bad parties can mess with the launch, and they're using distributed ledger as the way to do that and to assure flight operations. I think that's a great point. It shows the power of the technology to create that access, but also to protect it at the same time and do it in a performant way. So it is there. It's just getting more of those cases out there. VW is using it to secure the odometer, so you can't, spoof the odometer in order to, when you go to sell or trade in your car. But at the same time, you can then use it. I know, but then they can use it to buy a slushie at the Quickie Mart.
Right.
So
Everything.
it's, it's a lot. It's pretty exciting as a transport mechanism that really helps multiple parties get together faster and easier than ever before. That's where it's really going to shift a lot of business models.
Yeah. I want to take a minute for a second and just see who's in the room right now. How many of y'all are actually working on technologies or working with companies that have technologies around sort of infrastructure issues and are doing things around chip development or compute or database software? Anyone in the room? Show of hands. Wow. Yeah. All right. A fair few of y'all. And how many of y'all are just wondering about the implications that all of these new computing paradigms will have for your businesses at large? There we go. All right. So what sort of implications do these kinds of technologies have for folks' businesses at large? Let's take the industrial use case. Like, how deeply do people need to go into developing local networks or having local systems or the edge, right? How far do the edge need to go, or will all of this be hosted by AWS ultimately or some other?
I think Daniel was alluding to this earlier, but some cases you need to put a data center on the edge. Like you can't take the data off premises. You need it to be secure. Sometimes you have machines that are throwing off very high frequency sensor data, multiple sensors that are running at megahertz type data collection levels, and you simply have to process that on the edge. And you actually do see AWS providing these solutions like Snowball.
Yeah.
Where they basically give you a piece of equipment that's essentially like a data center. You can load that whole thing up with software and just put it right on the edge. But there's also there's two ways to look at the edge. Like I look at the edge from the IoT type perspective, which is really like right on the edge device or right on the edge piece of equipment. But for someone like Verizon, edge means often something different. You're talking about the edge of the telco network, which is more like a metro area. But anyway, it's sometimes important to differentiate what kind of edge. But
sure. Yeah. I mean, when you've made a couple of investments around these edge networking, specifically the use case of autonomous vehicles with Venium, right? That's
right. Yeah, Venium. I think back to the continuum idea is. I think there's always just going to be this decision on how do you kind of split the data to go where it needs to go, and some of it's going to need to be right there, local. And today, I don't think we do a good job of it's either now or slow, right? And I think the spectrum of what you're going to do is like for a car, you say, like, okay, a software update. I don't need that today, so I can do that on, whenever the network has space, I can do that. I can update the vehicle. If one vehicle saw something that completely blew the algorithm, that probably needs to go up to the cloud as fast as possible to try and,
retrain models.
Exactly. Yeah. And then there's probably, an accident here, so avoid this for traffic. And there's just a continuous spectrum of where you want the data. So Venium allows that to kind of shift, and it's somewhat network agnostic as to where it goes, but it's just how do we get the relevant data where it needs to go as fast as and efficiently as possible?
We have about 5 minutes left, and I think that's a perfect amount of time to dive deeply into quantum technology and the role that quantum compute is going to play.
Maybe a bit too much.
Right. I know, spoilers, there's going to be another session later that I actually encourage y'all all to attend that's going to be really taking a deep dive into quantum. But it's a fascinating area, and it can be really revolutionary from what I understand of it. But Mike, I'm going to let you draw the short straw and take a stab at explaining what exactly people mean when they talk about quantum compute.
And there's a lot there. So again, go to the panel later. Hear the real folks. But the key, right? Current compute, right, is binary 1 0, right? You're on or you're off. That's the whole transistor. It's a switch on off. And so everything from there comes from Boolean logic, building all the way up to all the applications we use. Because of the funny physics of quantum, the bit, instead of being 1 or 0, can be 1 and 0 at the same time. And so therefore, it's called being in all states simultaneously. And as a result, if you think about, let's go to the case everyone always talks about with encryption, if I have 128 bits for my key, there's 2 to the 128th possible combinations to find the one key. But with quantum, if you have 128 qubits, which are the quantum bits, because they're 1 and 0 at the same time, they're in all 2 to the 128th states simultaneously. So instead of having to calculate till the end of time to crack it, which is why you can't crack classically 128-bit keys, quantum, 1 clock cycle, all the states, so you have the answer in 10 milliseconds or 10 microseconds, whatever the clock cycle is, you have the answer. That's why, as a simple example, so it's that parallelism that is what's so powerful. And in the near term, with the quantum computers like from IBM, D-Wave, and others, in the short term, they're not big enough yet to crack that problem. In fact, I think most people say we're about 10, I'm looking at Carl, my quantum expert in the back, about 10-ish years away from doing that problem. But because we have 10, 50, 75 effective qubits, optimization problems in the short term are where we're going to see that application. So when you talk about AI, actually Google used quantum optimization when the original Google Glass, they were trying to come up with an algorithm to recognize a wink, not a blink.
Right.
And they used quantum to find the model. So it's going to really accelerate some of the AI because of that optimization.
And with that wonderful description, now that we only have 2 minutes left, I want to talk about how quantum is going to impact all of your businesses going forward and how you sort of develop new hardware or architectures around a quantum computing paradigm. So moving up the stack, what does that mean? What are the implications for Intel? Are you thinking about investing around that?
We have internal research and development going on quantum computing and have for some time. And see advantages of it. Honestly, with my focus on the edge, I'm not really the expert. I don't know, Daniel. Do you have any thoughts?
No. I was going to make sort of a general comment. It's really. Us VCs are really, really wonderfully awesome at getting super excited about the latest shiny new thing. And then we go invest in 1 million of them all at the same time. And so that's a precursor to saying that I believe in quantum computing, and I think it's actually a thing. And people have been working on it for 20-ish years, and people are going to be working on it for another 20 years. It's not going to be here next year.
Right.
It's not going to be here the year after that.
Right.
It's not going to be here the year after that. It's not going to be here the year after that. But at some point in time, it's going to be here, and it's going to be really cool and really powerful, and there's going to be some awesome use cases.
Nothing that has any implications for your business at all.
I'm just saying it's.
No.
It's like everything else in the world. You get real super excited about it because it's really cool and it's disruptive as hell.
Right.
But physics. So one of the things I've learned in doing venture capital for almost 19 years. Physics problems are really hard. See the scars? The open wounds?
Well, I mean, I guess what I'm wondering is whether there are going to be these sort of centers of compute power ultimately that understand quantum.
Okay, well,
and
that's
do quantum as a service for other people.
That's a really good question, and maybe I'm not sure if you're going on this direction or not, but I think one of the things that
You're assuming I have a direction.
Oh,
Let's
shit.
all right, that's
So one of the things that I think we maybe all collectively as a group together have to be concerned about to some extent is the amount of power, let's use that word, or collective intelligence that might be in the hands of a very few people. And that's not just about quantum computing, although quantum computing is already going that direction for sure, without a doubt. But if I think about machine learning and deep learning expertise in the world, I can assure you that if we did a heat map of where that was located, there'd be about 3 places that have a overwhelming, dominant amount of deep learning, machine learning, unsupervised learning, supervised learning, continuous learning, AI intelligence. And it's in the hands of about 3 to 5 maybe places on the planet. And that is something that I think we should all collectively be concerned about. I don't know if you were going there, but I thought I'd just take it up a notch.
No, I mean, I think that's great. Unfortunately, we only have 30 minutes, and that's another 30-minute can of worms that you just opened right there. But these fellows are going to be
Jeff needs a chance to talk.
Well,
Yeah, well, I could top that. I don't know.
do you want to talk about those 3 power centers? And
No.
no, I think we are out of time. Sorry, Jeff. But these guys are going to be around for the rest of the day or for part of the day to talk to y'all. And I will as well if you want to talk to me, although I know less about this than these folks do. But thank you so much for listening. It was a hell of a time up here, fellas. Thanks. Appreciate it.
Thank you.